Good afternoon, gentlemen. Mr. Ealing in particular, I hope I pronounced your nom de plume correctly. This video is for you, sir. Let's talk about buses and bus masters and bus arbitration protocols and shit like that. So, I am by no means an expert on the subject. I'm just a dumb, dirty hick that lives in a shack and farts around with old computers. So anything that I say could be just as valid as the 2020 election. So just saying. Alright. Alright, so the bus. I don't know where you sit on the ladder of learning here, so I'm going to kind of start at the beginning, so I hope that doesn't bore you to tears. The bus in the computer is, of course, the pathway by which all of the different devices within the machine move data between each other. The CPU, the memory, your input-output devices, your disk, blah blah blah, right? And in essence, generally, the bus is really just a passive set of wires. I mean, some of them may have active termination. We can talk about that some other time if you'd like. But there's generally not much logic on the bus. It's just a set of wires that data goes onto. Some device will put data on the bus and some other device will read that data off of the bus. Like your PC motherboard, you know, that's got its expansion slots in it, and all this other shit on it, you can envision that, pardon me, if you will, as a board that combines both a passive ISA backplane and a CPU card. Which I was going to whip one out of, but they're all installed in a computer at the moment, so I'm not going to do that. Alright. The question then becomes, how do we decide who is in control of the bus, that passive data transfer set of wires, and who's going to be reading and who's going to be writing, and what happens if more than one device in the system wants to use the bus, and etc. ad nauseum. So this is where bus arbitration protocols come into play. So the general computer bus is actually made up of three, what shall we call them, sub-buses. There's an address bus, which if you'll recall, we're going to pretend that all CPUs are memory mapped right now. That's actually not the case, but it makes the explanation easier. So forget about I/O space. I/O access and memory access are basically the same. I mean, some of the bus timing is a little different with some CPUs, like the Z80 inserts an extra clock cycle in I/O accesses and stuff like that, but the principles behind them are the same. There's just a line that says, oh, this is a memory access, or oh, this is an I/O access. And then other CPUs like the 6502 and the 68000 don't differentiate between memory and I/O space at all. Just everything's memory. If it wants to, write bytes to a serial port, one after the other, there's just a memory location that you write those bytes to, and they go into the serial chip. Right, so there are generally three sub-buses that make up the general purpose computer bus. The address bus, which tells us which chunk of memory or I/O we want to access, and we'll use 8-bit CPUs in this case because they're a little simpler. So with a 64K 8-bit machine, we'll have 16 address lines. That's enough for 65,536 little memory locations, starting at 0 and ending at 65,535, right? That's but we don't call it a 16-bit computer. It's still an 8-bit CPU because the next sub-bus, we'll call this the address bus. Address bus. Alright. There, I made a pretty arrow and shit. The next sub-bus, or whatever you want to call it, is the data bus. And this is where we generally get the width of the CPU from. This is the data that's going into or out of whatever location is pointed to by this binary number contained in this 16-bit address bus. And it'll be 8 bits for an 8-bit CPU. It'll be 16 bits for a 16-bit CPU. It'll be 32 bits for a 32-bit CPU. It'll be 36 bits in a PDP-11. What? Yes. And so on and so forth. So we have our data bus. And we're going to draw it a little bit differently. Oh my god! It's got an arrow on each end. Yes, that's because the data bus is bidirectional. Data can go out of the CPU on the data bus, or it can come into the CPU on the data bus. That makes things a little funny, but we'll talk about that later. And then the final sub-bus that we generally call a control bus, and it contains all of the miscellaneous lines that describe how these addresses, how this address and data are supposed to be interpreted. So for example, on the Z80 and the Intel CPUs and all of the other IO mapped CPUs, there will be a line that goes high, for example, if we're doing a memory access, or low, for example, if we're doing an IO access. That may not be the case. I can't remember which way it works on those CPUs. The Z80 has two different lines, a line for memory and a line for IO, and I think the Intel CPUs have one that goes back and forth. I can't remember. I may be full of shit. And, you know, then there will be a read-write line that tells us what direction the data is going on the data bus. Like, for example, if the CPU wants to write to memory, we'll put the CPU on this side, and we'll put the memory on this side. Oh, shush, phone. If the CPU wants to write to the memory, this read-write line will, for example, go low, and the data will be placed on the bus by the CPU. That means it will drive voltages onto these data lines. The CPU is always driving the voltages on the CPU will be driving voltages onto these data lines. The CPU is always driving the voltages on the address lines, unless it's not the bus master. But we'll get to that after a while. Right. Or, you know, if the read-write line goes high, plus 5 volts instead of ground, then it switches direction, and that tells the memory to place data onto the data bus, represented from whatever location the CPU is pointing to with the address lines, and then the CPU reads those voltages off of the bus. It reads its 8 bits off of the bus that way. So we've got the control bus, and the control lines go both ways. And they're just a bunch of the control bus is everything else. Your reset line, your read-write line, your memory I/O line, the bus arbitration lines, the bus request and bus acknowledge lines, the interrupts, etc., etc. So we'll call these control bus, and we'll make it a little smaller, because there typically aren't quite as many control lines as there are especially address lines. Right, so this is all well and good if our computer only consists of a CPU and some RAM, but a computer that only consists of CPU and RAM isn't going to do much. Even if you have some front panel with which you can key stuff directly into memory and then soft reset the CPU so that it'll start running, there's no way for it to actually do anything useful. It can't interact with the outside world in any way. So to do that, we have to add more devices to the bus. We can add a video card so that we can display shit to a screen. We can add some port that we can read from to read data from a keyboard. We can add a set of ports to control a hard disk drive and shit like that. And in general, in those situations, in most simple 8-bit computers, the CPU is always in control of the bus. That is, the CPU is always the one that is asserting voltages on these address lines. It's controlling everything else, every other peripheral in the system all the time. Alright? It's in control of the address bus. It provides the clock to everything else. It's the big cheese, you know what I'm saying? And that's fine if you've only got one CPU. Or if you don't have, say, a video card that wants to do some kind of really fast read of a big block of memory into its own buffers so that you can, say, blit some sprite to the screen without, you know, like a byte every clock cycle instead of taking like 8 or a dozen clock cycles to write a memory location with the CPU. That's what we call DMA, or direct memory access. The concepts behind doing DMA are the same as, well, not the same, but extremely similar to, like, what happens if we have, you know, more than one CPU in the system that wants to access the bus. So in general, we're going to treat them both the same, even though they're not really quite both the same. But if we've got more than one CPU, let's just call it more than one device in the system that wants to take control of the bus and drive these address lines and drive these control lines and act like the CPU, then we have to have some way for that device to tell the CPU, dude, quit putting voltages on the address and the control bus. Let me do it instead. Just unhook yourself from the system, and I'll pretend that I am the CPU for a little while. Does that sound good, buddy? And then the CPU, it's probably in the middle of something when this device decides that it wants to do this, so it can't just drop whatever it's doing at a moment's notice and be like, sure, whatever you want, bub. So the peripheral, let's call it the peripheral. Oh fuck, I can't. The thing. I can't spell. The thing is also on the bus. The bus goes underneath of all this stuff, right? The thing has to be able to say to the CPU, I want to control the bus. We'll do this through a line on the control bus called the bus request line in general. And so the thing will assert this bus request line, and the CPU, which is probably in the middle of watching porn or something like that, has to finish what he's doing before he can let the thing go ahead and access the bus. So the CPU will finish whatever instruction it's executing or whatever bus cycle it's doing. Sometimes, well, no, you can't really interrupt him in the middle of an instruction. It completes its bus cycle, which may be multiple clock cycles, and then it disconnects itself from the bus. That is, it's not driving any voltages, ground or 5 volts, onto the address lines or the control lines that go this way, right? It completely disconnects itself from the bus, but then it asserts a bus acknowledge line, which tells the thing that it's off of the bus, and it can do whatever the fuck it wants with the bus. So then the thing can start acting like the CPU, and do whatever it wants the same way that the CPU would. And when it's done doing its thing, this differs between different architectures. So this is the Bus Arbitration Protocol that we're talking about right now, and it differs a little between different architectures. So this may be true for some CPUs and may not be true for others, or maybe it's not true for any CPUs, and maybe I'm confusing more than one CPU and feeding you a line of shit. But in any case, when the thing is done acting like it's the CPU, it unasserts that bus request line, which tells the CPU that, I can be the CPU again, I can take control of the bus, and then the CPU deasserts that bus acknowledge line and continues to operate as the bus master again. This thing was the bus master after it requested the bus and the CPU granted it, and then when it was done, the CPU becomes the bus master again. But in all of these cases, the CPU was the arbiter of the bus. Alright? The CPU is the big cheese that decides when everything else can be the bus master. And this is how it works on single CPU systems. But when we get into symmetric multiprocessing, there isn't any CPU core priority going on. They can request the bus willy-nilly. and that makes that arbitration protocol a little more complicated. Now, I don't know much at all, if anything, about the details of how SMP works, but if you want to study up on let's call it a symmetrical bus arbitration protocol that doesn't have, like, well, there is an arbiter on the VME bus, but your primary CPU doesn't have to be the bus arbiter. You put it like whatever you put in slot 0 of a VME bus machine is the bus arbiter, right? And then so usually that's the primary CPU card, but it doesn't have to be. Right, the VME bus is kind of interesting. VME bus is basically the Motorola 68K bus, that's how bus arbitration works. I've probably butchered the fuck out of this. I hope not, because I don't want to lie, but I may have. And as far as synchronous and asynchronous buses, which I think we were also talking about in that video that you were asking about, a synchronous bus, and on a synchronous bus, all of the peripherals operate at the same clock speed. There's a master clock provided by the system, and all of the peripherals operate in lockstep with that clock. And like if you've got memory or your thing. If your thing is slower than the CPU, then it has to be able to assert some signal telling the CPU that it's not ready for the CPU to read that data that this thing is supposed to be providing to the CPU, or that it hasn't had time to write it into its whatever internal thing if the CPU is the one providing the data. So on the Z80, that's what the wait line is for. The CPU, it'll say, like, give me the byte at location 5 or something, right? And then whatever thing, whether it be memory or peripheral or whatever at location 5, if it can't immediately provide that data to the CPU within, the next clock cycle, it can assert that wait line, in which case the CPU just spins in circles until the thing gets its data ready and puts it on the data bus, and then can deassert that wait line. So that's the way that a synchronous bus can handle slow peripherals that are slower than the CPU. Now, that's the case with the Z80. The 6502, it doesn't have the ability to do that. I think to insert wait states on a 6502, you'd have to do some kind of clock stretching, which is, I think, what the 6502 VME bus boards do, but I've never messed with any of those. But no, like the 6502, it doesn't support wait states like the Z80 does. I don't think. The very newest 6502 might. I think the 65816 does, but don't quote me on that. And then, so those are all examples of a synchronous bus. Everything operates in lockstep with that clock. But then we've got CPUs like the PDP-11 or the Motorola 68000, which is kind of based on the PDP-11, that have a completely asynchronous bus. There's no clock. Well, there doesn't have to be any clock supplied by the system for the whole bus to run in lockstep. Everything operates on those handshaking lines that are kind of similar to those bus request lines in the way that, something will assert something and something else will assert something else, saying that, yes, I saw that you wanted something and I'm ready, right? So like when a Motorola 68000 wants to access memory, it says, I want to access memory. And then the memory puts its data on the data bus. However long it takes for it to do it, it can do it instantaneously, or it can fuck around and read something off of a disk before it does it. It doesn't matter. But when it gets that shit ready and puts it on the data bus, then it asserts another line that says, yes, the data is there, and the CPU reads it, and then it deasserts its shit, and execution continues as normal. Now the CPU is clocked; it runs at a certain clock speed. Its internal like computational logic runs off of a clock. But as far as its external bus that accesses the memory and all of the peripherals, it doesn't have to be asynchronous. But the Motorola 68000 does support a completely asynchronous bus like that, that allows us to. It requires more logic to interface with a bus like that, because like your memory, for example, you have to have some kind of delay line in there so that that line that says yes, the data is ready doesn't get asserted before the data actually is ready. You know what I'm saying? So it makes the bus interfacing a little more complicated, but the advantage of it is that you can it makes it easier in a way to mix and match slow and fast CPUs and peripherals on the same bus. So, all right. Did that make any sense, or am I full of shit? I hope I didn't tell too many lies in that. Like I said, I'm not an expert. I'm just a dumb, dirty hick that lives in a shack and farts around with old computers. So, if you want more information, I can't remember the names of any of the books, but if I'm not feeling too lazy after a while, I'll go look at my bookshelf and suggest some book titles down in the video description if you're interested. Alright, that's all for that. I've got to get back to work. This was a somewhat long lunch break, so see you all later. Thanks for joining me.